Lab next week is focused on a concept called Hess's law. But before we can get into activity 10B, there's just a few things you need to know because we have not yet finished 10A, and you're going to need to know some things in order to understand what's in this activity. On Wednesday in class, we talked about heat. We give heat the symbol Q, and we looked at examples of heat being transferred from one object, like a block of metal, into another object, like a mass of water. We have not yet started really talking about the heat that comes from a reaction or that is consumed by a reaction. But under the situation where a reaction is done at constant pressure, then the heat that is transferred from or to the reaction is given a special name. And it gets this symbol here, delta H, which is change in enthalpy. H is enthalpy. But for the purposes of what you need to understand, what you just need to know is that enthalpy, or the change in enthalpy, corresponds to the amount of heat that is either given off by a reaction or absorbed by a reaction. Okay, so with that, let's get started. So let's look at model 1. Delta H enthalpy of a reaction, I'm going to put reaction as a subscript there, is also sometimes called the heat of reaction. So the enthalpy of reaction, the heat of reaction. So we've got here 3 reactions. They were performed under conditions of constant pressure, and the heat produced in each case was measured. Now what we can see is that the sign convention that we learned for heat the other day holds true. So this delta H of reaction has a negative value. That means that this reaction is exothermic. This one is also exothermic. So these 2 reactions actually did give off heat. This one, however, has a positive sign. So that means that when you do this reaction, it actually consumes heat energy. Okay, so let's look at the questions. How much heat was given off when 1 mole of hydrogen gas was burned under conditions of constant pressure? Well, burning just means combustion, reacting with oxygen. So we can see 1 mole of hydrogen, when that reaction occurs, this is how much heat is produced. And again, the sign here, negative, just means that it was given off. What is the delta H for the combustion of 1 mole of hydrogen gas? That is minus 241.8 kilojoules. What is the relationship between delta H of reaction, or the heat of reaction, and the heat given off at a constant pressure? Well, they're the same. Provide an answer in words and in an equation using the symbol QP to symbolize heat given off at constant pressure. So as we said earlier, QP, the heat transferred at constant pressure, is equal to the enthalpy of reaction, or the heat of reaction, and that's the heat transferred at constant pressure. Now, it says in question 4, describe reaction 2 in words. So reaction 2 is 2 moles of hydrogen plus 1 mole of oxygen produce 2 moles of water. Is reaction 2 the same as reaction 1? Well, definitely not, because it's got different number of moles involved, but it is the case that the quantities, or the reactants and products, are the same in both. It's just that this is a scaled up version. Reaction 2 is a scaled up version of reaction 1. How does the heat produced by reaction 2 compare to the heat produced by reaction 1? Well, let's look. 241.8 or 483.6 looks to me like this is a factor of 2 greater. And notice that this was also a factor of 2. So the heat produced by reaction 2 is twice as much heat as reaction 1 because there are twice as many moles reacting. So if we multiply all the coefficients in a balanced chemical reaction by some number, how can we determine the delta H of reaction for the new reaction? Well, if we've multiplied by some number, like we did here, we multiplied by 2 to get from reaction 1 to reaction 2, then we would also multiply the enthalpies by that same number. So we would multiply the original delta H of reaction, or heat of reaction, by the same number. Now let's look at reaction 3. How would we describe that one in words? We could say that 1 mole of water is broken apart into 1 mole of H2 and a half a mole of O2. Is reaction 3 the same as reaction 1? Well, if you go back and look at it, you'll see it has the same compounds involved, but they're reversed. So what were reactants in reaction 1 are now products in reaction 3 and vice versa. So how does the heat produced, and produced here is in quotes because as we said when we started this, that's an endothermic process, so heat actually is not produced in this case. But how does the heat, the quantity of heat, compare to the heat produced by reaction 1? Well, it's the same quantity, but it was positive. In other words, it was consumed because the reaction is going in the opposite direction. One way to think about this is that if a reaction produces heat in one direction, you can think about heat as a product, and if it reverses, then you have to think about heat as a reactant. So if you reverse a reaction, how can you determine delta H for the new reaction? You're just going to change the sign of the heat of reaction. Now let's apply what we've just learned to a new situation. When 2 moles of carbon dioxide are decomposed into 2 moles of carbon monoxide and 1 mole of O2, 566 kilojoules of heat are consumed. Let's write out how we would display that from a chemist's standpoint. So I'm going to write the reaction, and then I'm going to write the delta H of reaction off to the side. Now there's one thing I just want to make sure that we're all on the same page about, and that is the sign of the delta H. Because we were told heat was consumed by this reaction, that means it's an endothermic process. It absorbs heat. And so the delta H of reaction is going to be positive value. So now, what would be the delta H of the reaction of CO plus 1/2 O2 going to CO2? So let's first of all notice that the reaction switches the reactants and the products compared to the one above. So let's take care of that first. So we're in our first step here. All I've done is I've just written the reaction in reverse, and as we learned from earlier, if we're going to reverse a reaction, switch its reactants and products, then the sign of its enthalpy change will be reversed. So if we go in this direction, it's an exothermic reaction. But we don't want these quantities, we want a process that has half as much. So let's write that and figure out what its delta H of reaction will be. Okay, so let's see what I just did here. Notice that going from here to here, I divided by 2. And so that means if I'm going from here to here, I also need to divide by 2. So the enthalpy change for this reaction, which is what question 13 was asking for, would be minus 283 kilojoules. So let's stop for a minute and think about what that whole model was about. What that model was about was helping us to understand if we do a reaction in one direction, and we know its enthalpy change, and we consider the hypothetical scenario where we reverse it, then we would reverse the sign of the enthalpy change. And the other piece of information that we now have is that if we scale up a reaction or scale down, then we're going to scale up or down accordingly the amount of heat involved in that process. Now, why is this handy? Well, it turns out that if we know how to manipulate equations and their enthalpy changes, we can often figure out what the enthalpy change is of a reaction. So we've got 3 reactions, all performed under conditions of constant pressure in this model, and we've got the heat produced. And in this case, all 3 of them are exothermic, so that's true. Heat was produced in all 3 cases. So how much heat is given off when you combine 1 mole of carbon with a half a mole of oxygen gas to form 1 mole of carbon monoxide? So that looks like reaction A, and so I'm going to say the heat of the reaction is minus 110.5 kilojoules. Note that sometimes when people ask how much heat is involved, they really want the absolute value, but I like to keep the negative signs to make sure that we're clear that this was heat that was given off. Likewise, how much heat's given off when you combine 1 mole of carbon monoxide with a half a mole of oxygen to form 1 mole of carbon dioxide? Well, we have that number here. Okay, so far so good. Question 16 asks, how is the overall process of reaction C related to the individual steps in reaction A and B? Now I'm going to write down an answer here in a minute, but what I suggest is that you really stop and study reactions A, B, and C and see if you can figure out, before I do, what the relationship is between A, B, and C. So what I wrote is that reaction C is the sum of reactions A and B. In other words, if you add up all the reactants and add up all the products for A and B, what you end up with is reaction C. You should go back and verify that you believe that. So if reaction C is the sum of A and B, then how is the enthalpy of the reaction for C related to the enthalpies of reactions A and B? So we're going to write out what's happening, but let's think about this. If in step A, reaction A, we get a certain amount of heat out, then we do a second step by doing reaction B and we get another amount of heat out. Then if C is the sum of those two steps, then we should get the heat of reaction for A plus the heat of reaction for B is going to be the heat of reaction for C. So how might we write in a complete sentence a description of how the enthalpy of a reaction for an overall process is related to the enthalpies of reactions for individual steps? So the way I would write this is the enthalpy of reaction for an overall reaction is the sum of the enthalpies of all the steps. And this is in fact a statement of Hess's law. Hess's law states that the change in enthalpy for a stepwise process, in other words, something you do step reaction A first and then do reaction B, is the sum of the enthalpy changes for the steps. Let's now consider three reactions, L, M, and N. We're given the reactions and we're given the enthalpies of reactions, the heat of reaction. We want to use this to determine the enthalpies of reaction for each of these, which are going to be related to the reactions above. So let's take the first one. If we are interested in carbon plus oxygen going to carbon dioxide, well, that's the same as reaction L, so we already know the enthalpy change. What about CO2 going to carbon monoxide and half a mole of oxygen? Well, we don't have any examples here where CO2 is a reactant, but we do have a couple where CO2 is a product. Now we want something where CO and O2 are involved. So that looks like probably we're looking at a rearrangement of reaction M. If we were to rearrange reaction M and at the same time do it on half the scale, we would end up with this reaction here. And we did this once before. So if you go back to Model 2, you'll see that we've already done this once. And what we found was the enthalpy for reaction was 283.0 kilojoules. So this is half of reaction N in reverse, which is why it has a positive value, because we reversed it. And then it's half of this, which is where we get the 283. And the reason it's half is because we're doing that on half the scale. So we're not doing 2 moles of carbon dioxide to 1 mole of O2 and 2 moles of CO. We're doing 1 mole of CO2 to 1 mole of CO, a half a mole of O2. All right, the last question is water going to H2 and O2. Now we don't have any example where water is a reactant up here, but we do have one where it's a product. So envision that we're going to reverse this one, and then it also looks like we're going to do it on the half the scale. So let's go ahead and do that. I'm going to write it out here just to be explicit. So the first step would be involving just reversing it, making the reactants into products. And when we do that, we have a new delta H of reaction. Since all we did was reverse it, in this case, all we need to do is change the sign of our delta H of reaction. But we don't want to do it on this scale. We want to do it on half the scale. So let's change that. So since going from here to here, we had to divide by 2, then that also means we're going to have to divide the delta H of reaction by 2. And so what we fill in our answer to 19 is 241.8, which is really half of reaction N in reverse, which makes me realize that there is a problem in what I wrote above. This should be reaction M here. Now, if we look at these 3 steps and we envision that we're going to do these 3 steps, let's say on day 1 we do this reaction and it produces this much heat. On day 2 we do this reaction and it absorbs this much heat. And on day 3 we do this reaction and it absorbs this much heat. We might say, well, what's the overall chemical change that we have produced? And that's what question 20 is having us think about. If these 3 steps would be considered as individual steps for an overall process, what is the overall process? So here's how I think about going about this. We're going to make this into a little addition problem. And let's look at all of the reactants here. And I'm just going to write them all down here. So I've got carbon, and I've got O2 gas, and I've got CO2 gas, and I've got water. Those are all my reactants. Now, if I now take all of the products and I write those down, what I get is CO2 gas plus CO gas plus 1/2 O2 gas plus H2 gas plus 1/2 O2 gas. So that, I could say, well, that's the overall thing that happened. I used up all these reactants and I got all these products. But there's a simpler way to represent this. So for example, let's combine these 2 O2s and let's recognize that we used up a mole of CO2 and then we got it back. So in terms of a net change, we didn't actually change anything in terms of CO2. If we combine these 2 moles of O2 into 1, we can see we used 1 up in the reactant, so the O2s also are going to drop out. So what would be the overall process? So here we are, carbon plus water going to carbon monoxide and H2. If we did these 3 reactions, 1 a day for 3 days, this would be the overall process that would have been accomplished. So now what is delta H for the reaction of pure solid carbon with water to form carbon monoxide and hydrogen gas? Well, what we learned earlier is Hess's law says that if we have an overall process, which is what we just determined in question 20, then the enthalpy change for that process is the sum of the enthalpy changes for all the individual steps. So let's go back to question 19, write down what those are, and figure out what the enthalpy change is for the overall process. So we see, again, thinking about this as a stepwise process, if on the first day we got out minus 393.5 kilojoules, on the second day we absorbed 283, and on the third day we absorbed 241, then the net heat change is 131.3 kilojoules. And so the powerful thing about Hess's law is we could say, you know what, we could just do that reaction in 1 step, as we wrote it in question 20. And if we did that, then that process would be an endothermic reaction that would absorb 131.3 kilojoules. What's powerful about Hess's law is the ability to calculate the enthalpy change for a reaction without having to measure it if we know enough about some other kinds of reactions to be able to predict the enthalpy change for a new one. I'm going to stop here because this ends, Model 3 ends the material that you need for the lab.